Hey guys, it's Mr. Sheeline here. This is going to be the Unit 4.2 notes covering velocity and motion. This video is going to include both just me reciting and talking about all the things in the notes, and it's also going to include the answers for the check your understandings, okay? Okay, so let's just go ahead and go through these. Come on. Okay, so here are your learning objectives for this set of notes. So what I expect you guys to come out of this unit section is that you can differentiate between distance and displacement. You can identify a vector quantity, and you can calculate velocity using displacement and time. Okay, now before we get into what velocity is and whatever displacement is, just remember, we're still working with one-dimensional motion here. Okay, so we're still working with motion that's on a single plane. Okay, we're on the x-axis, we're on the y-axis, we're going east-west, we're going north-south. That's what we're still doing here. We're not adding a second direction here to complicate things. Okay, so this is the same exact slide that I ripped from the previous note section. So it's like a man walks eastward at a rate of 2 meters per second. Perfect. That's one-dimensional motion. Okay, and then the car example you can read there as well. Okay, why do we have two? I must have been thinking to make something and I just didn't make it. That's weird. Whatever. So anyway, one-dimensional motion. Remember, we're still working with uniform motion and non-uniform motion. Pretty much all you need to know about uniform motion is it's motion at a constant rate, meaning that you have a constant speed, or what we're going to get into, constant velocity, and they're going in a straight line. They're not changing direction. Non-uniform motion is movement that does change its speed and also changes its direction. So we're still working in these bounds, okay? And it's important to understand that speed works in these bounds, velocity works here too. It's just now we're going to be getting into seeing what the difference is between speed and velocity. Now, the velocity is super duper duper similar to speed. The only difference is what you can see here in the definition. Velocity is the rate of change of position with relation to the direction it changes. That's a fancy way to say that velocity relies upon direction to define it. So what we're focusing here is that speed is the measurement of how fast something is going, no matter the direction. Velocity is more or less the speed, but with direction. We care about direction now. That's what velocity is. And we're going to be just kind of really simply working with velocity, which you kind of already have with speed, to be honest. Okay, it's just we got to add a couple things now. So it says here that velocity relies upon direction to define it. So because we have to rely upon direction, velocity is what we call a vector quantity. So if you remember when we were looking at speed is a scalar quantity, meaning that we only care about the magnitude. We don't care about direction. All we care about is that, well, how quick is it moving? Okay. That's all we care about. Now, with velocity, what we care about, well, how quick is it moving and what direction is it moving in? Okay. And more importantly, is it going to change directions? Okay, because if it changes directions, then we have a bit different calculations to make. So anyway, here's the definition of vector quantity. So remember, you need to know what a scalar quantity is. You need to know what a vector quantity is. Vector quantities are measurements that have magnitude, so that has size, and it also has direction. So examples of what that would look like, it'd be like kilometers per hour up, meters per second to the right, miles per hour to the west. Okay. So it's the same units. We're using the same units as we are with speed. The only difference is now we just have to tag on this little note about the direction they're moving in. Okay. Now to calculate velocity, we need two things. We need displacement and we need time. Now we're going to talk about displacement a good bit because we need to know what it is and we have to have a pretty good idea of how to use it. And that's what we're going to practice with first before we get into velocity, because you need to know what displacement is. You need to know what it is and how to find it, and its difference with distance. So displacement, as it says here, we measure this in meters or kilometers with the direction the object is moving. And then the time here we use, like we do with speed, it's seconds and hours. Let's go over the symbols like we did with the previous note. So velocity, I'll just say actually before saying it, hopefully you should notice that these are pretty much the same as speed. The only difference is the arrows above the V and the D. Okay, so velocity has the symbol V with an arrow over top. Displacement has a symbol D with an arrow over top. Time is the same. Time is just going to be T. Okay, time doesn't change in between speed and velocity. It's pretty much the same regardless what you're trying to calculate. So notice the arrows on the V and the D for the symbols for velocity and displacement. Now, why do you think we would use these arrows for the symbols? So take a second, think about that for a second. Why would that be important? Okay, just think about that for a second. Why would the arrows on the V and the D be important? Well, they're important because we're using, for the most part, one, we're using the same symbols, right? We're using V and D, and we don't want to get them confused with, the V for speed and D for distance. Sure. But more importantly, this is showing that we're making a distinction between a scalar quantity and a vector quantity. We're saying that here we're calculating velocity. Well, how do I know? Because I'm putting the arrow on top. So I expect to have my answer with a direction labeled after the units. Okay, so we use these arrows to indicate that this is directional, that we care about direction, that they are vector quantities, that we're working with velocity and we're working with displacement. Okay. So we're going to be doing this for both velocity and also displacement. So because we care so much about direction, we have to put the direction in brackets at the end after the units. So it would be like all of these examples here. So it'd be like, say, velocity, well, it's 5 meters per second to the east, or it's 10 meters per second to the east written this way, or it's 15 meters per second upwards. It's 20 meters per second down. So these are all the ways that we can write this. What's important is that when we write our answers, let's see, get my toolbar back. Of course, I can't get it back, or whatever. But what's important here is that you have the brackets, you have your direction, and then you end the bracket. Okay, so you want to that's where we're going to be practicing this a little bit here. So displacement versus distance. So what is displacement? Well, displacement is the comparison between an object's beginning position and its end position. So with distance is simply just how far did you walk, regardless of direction, regardless if you turned around, regardless if out of anything, regardless if you stop for a second. How far did you walk? What was the total distance that you traveled? Displacement does not take into account every single meter, every single yard or foot that you just walked or ran or traveled. It's only concerned about where did you end in relationship to where you began. Okay? So we only count where we started and where we ended. So meaning we are going to measure the distance between our starting point and our ending point. Okay? And we're also going to include the direction at the end of the value in brackets, just like you saw on the slide before. So here's a great example. So we would say, if we had to calculate displacement, we'd say, we calculate it and say, displacement is equal to 50. Oops, I forgot my units. It should say 50 meters north. If I have my toolbar here, let me get my toolbar real quick. Okay. So I forgot the meters, and I'll make sure, I'll make sure that I get that changed. So it'd be like this. So it'd be, as soon as that little guy goes, a little M there for meters. Yeah, I forgot my units there. So it'd be like 50 meters north in this case right here. Okay. Okay. Now, in order to know the direction moving in relationship to our original position, or in order to know the direction moving in relationship to our original position and original direction of motion, we have to establish positive and negative directions, more or less. So what this means is that typically when we're practicing this, we do associate certain directions with being positive, quote unquote positive, some being quote unquote negative. All it means is that we have to establish that we're expecting our guy to move in this direction, and if he doesn't, it's going, you're subtracting, you're going the opposite direction. So typically in these practices, positive directions are up, right, east, and north. Those are typically what, and for the most part, most of your examples are going to start with your guy moving up, right, east, north. And we just keep it positive. We keep the numeral value of the displacement positive. Whereas negative directions, this is down, left, west, south, these are typically, it's to say that, well, if you moved east and then like 50 meters, actually, I think it's on the next slide. Let's take a look at that. Yeah, so it's to say this. So like to measure displacement, we can draw out the direction and distance, see subjects travel. Let's give this a go. So this is what I'm talking about here when we're going to talk about positive and negative directions. Now, the overall answer is not going to be negative. They'll always be positive, but that's where the direction, right in the direction the brackets comes in at the end. And so it's a little tricky here, but it'll take some practice, but it'll make sense here. So, but we can draw these out. So Jamal walks 50 meters east. So it's to say that, Jamal started here and he walked 50 meters east. He walked this way and he walked 50 meters east. Okay, that's what happened here. Okay. Carolyn runs 100 meters north, turns around, and then runs 25 meters south. So this is where I told you that direction is crucial and that we have to keep track of this, and we only care about the relationship, the distance between the starting position and the ending position. So it's to say this: Carolyn first ran 100 meters north. Okay, so we're going to say this is 100 meters north. And then this little lady turns around at this point, and then runs 25. Oops, and I'm going to actually, right there, I think it's good. Then runs 25 meters south. Okay, so what's the displacement? Well, she started here and then she ended here. So basically it's just what's the difference? What's the distance between, but I guess here and here, just so you understand, she's on the same, she didn't, walk over here because that'd be changing direction. She just literally turned around in the same line. So she's actually like right here. So what's the distance between here and here? Okay, and we'd find that by just simply doing 100 minus 25. So this is where the positive and negative comes in. So if Carolyn here were to run 100 north and then another 100 meters north, well, it'd be 100 plus 100, more or less. Okay, so you'd have a displacement of 200 meters. This case, she ran straight north for 100 meters, turned around, and then went south for 25 meters. So it's 100 minus 25, which means that her displacement is only 75 meters, and specifically 75 meters to the north. Okay, because she's still north of her beginning position here. Okay, she's still north of her beginning position here. So this is what we're going to be practicing a little bit with displacement, and a little bit, like very, very little. It's just for you to be aware of what displacement is. So don't feel like this is going to be super tricky. It's really not. It's if you draw it out, you'll be fine. If you can understand that I'm starting here, I'm ending here. What's the distance between my beginning position and my ending position? We'll be Gucci. We'll be all good. Okay. So let's just keep on going. So looking at these, so measuring displacement in these scenarios. So Job walked 50 meters north. What's his displacement? Easy peasy. His displacement is 50 meters north. Easy. Okay. Arya ran 20 meters east, turned around, and then ran 20 meters west. What's her displacement? Well, she started, let's say she started here. She ran 20 meters this way, turns around, runs another 20 meters back. So she's back to where she started. So what's the relationship between her ending and beginning position here? Easy. 0. Okay, she has no displacement. There is no displacement because she ended where she began. And again, we only care about the beginning position and the ending position. And then Jason swam 5 meters to the right, turned around, and then swam 10 meters to the left. What was his displacement? So we've got a guy here, started right here. He went 5 meters. He went 5 meters to the right. And then he turns around on the same line, and then he went 10 meters this way. Okay, so he's ending right here. Okay, and he went 10 meters to the left. What's his displacement? Okay, well, we started on a positive direction. We went 5 meters to the right, but then we went 10 meters to the left. So it's going to be 5 meters minus 10 meters, which is going to give us a negative 5 meters. Now, again, here is where we're going to talk about the positive and negatives direction. So because we established that up, right, east, and north are positive, while everything else is negative. Okay, if we have a negative number in our as our answer here, so like this negative 5, that means that we went 5 meters in the opposite direction to our positive or direction. So in other words, what that means is this: that negative 5. That means that our displacement that we just calculated, our displacement here is actually 5 meters to the left. That's what we're saying here. So because we got a negative number in our answer, that means that it's no longer to the right anymore. It means that our answer is to the left, like right here. Okay, right there. So this is what we're practicing with displacement. It's going to be fun stuff. So here's this check your understanding. So give this a shot on your own. Okay, pause the video, try it out, see if you get it right. Okay, so if you walk in a straight line north for 2,546 meters, what's your displacement? What you should get is that your displacement is equal to 2,546 meters to the north. So you've got to include this guy. That's the new thing we're throwing in here, is the direction. Okay, so we have to include our units, proper value, and now also our direction. So keep that in mind. If you run an oval track with the perimeter, where do you begin? What's your displacement? So it's to say that you ran around and you ended where you began, okay? So you ended it at the 350, or sorry, you ended it, we'll just say this is a 400 meter track. Let's say you ran 400 meters and you ended where you started. What's your displacement? So give it a try, see if you got it right. Okay. So what you should have gotten here is you should have seen that, well, we began, or we ended where we began, so our displacement here is 0 meters, okay? Displacement is 0 meters because it doesn't matter if we ran around a circular thing, it doesn't matter. We ended where we began here, so that means that our displacement is 0. If you drove 100 miles east, turned around, and then 50 miles west, what's your displacement? So pause the video here, see if you get it right. Okay. So if you drove, let's say that's 100 miles east, what time is that? And then you turned around and then you went 50 miles west. What's your displacement? Well, your displacement now, because this is where you began, this is where you ended, it'd be 100 minus 50. So that's a positive 50. So that means it's 50 miles to the east. And that would be your answer for this check your understanding. Okay, so that's displacement. So let's get into that velocity calculation. So as you can see, it's pretty much exactly like speed. It's just now we have to deal with velocity and displacement now. So we're working with directions. But other than that, everything else is the same. We use the same exact triangle. We use pretty much the same, operations here. The formula is all the same. So here it is, if you want to find velocity, V is equal to D over T. If you want to find displacement, it's velocity times time. If you want to find the time, it's going to be time is equal to displacement over velocity. Okay, so it's no different than what we were doing with speed. So let's give it a go. A dog runs away from you for 60 seconds at a rate of 5 meters per second forward. What is the displacement? Okay, so pause the video, see if you can calculate displacement, come up with the right units and also the correct direction. Okay, so we've got time here, 68 seconds. We have our rate, which is our velocity, 5.6 meters per second forward. And we're trying to find displacement. What is our displacement? So pretty easy here. So it's just going to be D, or displacement is equal to velocity times time. So it's going to be 5.6, my goodness, my stylus, times 68. So our displacement here So what we should get here is our displacement is 380.8 meters forward. Okay, it's forward because our velocity is talked about just in the forward direction opposed to the backwards direction. Okay, good. A dolphin swims in a straight line east for 604 seconds with a displacement of 205 meters. What is the velocity of this dolphin? Okay, so pause the video here, give it a try on your own, see if you get it right. Okay, so it looks like we've got time here. Time, the dolphin's going to go for 604 seconds, and it looks like that it is moving to the east, so and our displacement is 205 meters. So displacement is equal to 205 to the east. We're looking for velocity. So this one is just simply V is equal to D over T, which is going to be 205 over 604. So our velocity here is going to be equal to 0. Not going too fast here, 0.34 meters per second to the east. Okay, and that would be our answer, 0.34 meters per second to the east. Let's see. Yeah, this is the last one, so give this one a go. So a man ran 100 meters north, turned around, and then ran 300 meters south. And he did this all in 54 seconds. What was his velocity? So pause the video, see if you can figure this out. Okay, so this one, we first have to figure out what displacement is, because we don't know what it is. So he starts, we'll say he starts here, he runs, oops, that may be too big. So he runs 100 meters north, and actually I'm going to redraw that. So he starts here, runs 100 meters north, and then he turns around, and then he runs 300 south. Okay, so that would mean then that this guy first started 100 meters north, minus, it would be 300 meters south. So what we would have here is negative 200 meters, which actually just means, we've got a displacement here of 200 meters to the south. That's what it's saying here, okay? So our displacement is going to be 200 meters south. So displacement 200 meters south. And he did all this in 54 seconds. And we're trying to find velocity. What is our velocity? Okay, so we know it's going to be V is equal to D over T. So that's going to be 200, oh my goodness, meters over 54 seconds. So 200 divided by 54. So that's going to be here. We're going to say 3.7 meters per second. Now, we've got to, because our displacement's to the south, our velocity is to the south. So it'll be 3.7 meters per second to the south. Awesome. So I know it seems kind of weird. Well, Mr. Sheeline, why are we using, all the same time if we only care about where we ended to where we began? Well, it's a good question. It's more to when we get in, we'll be getting into acceleration, which is also a vector quantity, and direction matters all the time. Okay, direction matters all the time. And there are moments where you do have to take little snapshots of the time. There are times when you need to use certain amount of time and not use others. In this case, because we're just practicing this in its beginning, we're just going to use the total time. It's something called the average velocity, technically speaking. We're not really going to get into the difference between that and another type of velocity. We're just getting into velocity, what it looks like, how we can use it to eventually calculate in the future, how we can use it to calculate kinetic energy, how we can use it to calculate acceleration. So that's what we're building here, is we're building on how to solve for acceleration and also forces and kinetic energy in the future. Okay, well those are the notes there, guys. That should be all the notes. Yep, that's all the notes. So if you have any questions for me still, make sure you get a hold of me. If not, I will see you in the next one.